Okay, we had four mechanisms to make the non-LS communication possible. We covered three of them to some extent, and we were left with scattering. So we'll have a brief discussion on scattering first, then a couple of other short discussions we'll have today, and thereafter we'll talk about radio network planning for solar environment. Now, scattering will take place when the surface on which the electromagnetic wave is incident is rough. Rough means the surface has ups and downs, but small ups and downs. And there's a way to estimate whether these ups and downs are small or not. Okay, if the ups and downs are too small, okay, then you can consider it smooth. Okay, so there is a way to differentiate, and I mean, we're using the term protuberances here. Okay, protuberance means the extensions. Okay, so the ups and downs are just treated as small extensions or protuberances. So Rayleigh criterion is a way to differentiate whether the surface is smooth or rough. If it is smooth, then reflection will take place. If it is rough, then scattering take place. Okay. Uh, so uh, I mean, this HC, okay, is the critical height for the protuberances, and H is the difference between the maximum and minimum protuberances, as you can see from here. Okay, so HC is calculated this way. You have lambda divided by 8 sine theta I, where theta I is the incident angle. Like before, we consider the incident angle as the angle between the incident wave and the horizontal line. I mean, the surface of the object. Okay, not the line, not the ray of the incidence, and the line vertical, or normal to the surface. Okay, not the angle between them. Okay, it is rather the angle between the ray and the surface. So with that, HC you can calculate here, and if the edge of the surface is smaller than HC, then the surface will be considered smooth, otherwise it is rough. Okay, and you can also calculate a standard deviation, okay, for your age. And here is some example or sample values of age and for rough stone. Okay, the maximum, the H means the difference between maximum and minimum, and standard deviation, which is 12.7 here, and the standard deviation is 2.54. Now, another term you can use for the estimation of the scattered energy, okay, and it is called radar cross section. The term radar comes in here because radar uses actually the reflection from the object, but you can also think of it scattering. Okay, you have to get some power back from the object. The radar sends a signal, and it is incident on the object, the fighter or whatever, and then you get some power back from there. This power is received from which it estimates the position and the velocity of the object. Now, here the way you get the signal back can be treated as a reflection or scattering. Okay. Uh, so if I just call it scattering, okay, uh, the the bottom line is you need to get some power back from the object. Okay, however you get it, through reflection or scattering. So here we are calling it scattering. So the power density that you have in the direction of the receiver, when ratioed with the power density of the radio of the wave that is incident on the object, okay, then it is called radar cross section. And of course, the power that
Can you repeat the part of radar cross section?
Yeah, yeah. The radar cross section uh, uses the term radar because here you like a radar, you consider the power, as I was saying, that what happens in the case of radar. The radar has both transmitter and receiver. It transmits a signal, maybe a pulse, and that is incident on the object, and thereafter it comes back. The receiver then receives the signal, and depending on the delay, okay, if the object is close by, then the pulse will come back uh, shortly, right? So the delay can tell you the velocity of the signal is constant, say. So the delay can tell you how far the object was. Also, you may be sending, we will have a short discussion. We can have a short discussion on radar in one of our lab class. Okay. Um, because we have actually a radar in our lab, and we are planning to have a short video capture of in our lab and then show it here. So when you do it, we can have a short discussion on radar too. But the basic concept is very simple, as I said. You transmit maybe a pulse or some signal, and then when you get the pulse back, you can actually estimate the distance of the object from the time gap between the reception and the transmission. And if you are sending the signal in different directions, so out of them, when you get the signal back, okay, can tell you which way the object is. The radar, you may know that it has a directional antenna, but it keeps rotating. It keeps rotating. Okay, so in every direction, it transmits and receives, transmits and receives. When it finds some good energy in the received signal, okay, if there is nothing, then there won't be good reflection or scattering, whatever you say. But if there is an object, okay, which can reflect or scatter a good amount of energy, okay, that's an indication that you have something there. So you're rotating your antenna and in the direction in which you receive significant energy, you consider that you have some object there. And then between the time gap, okay, depending on the time gap, you can calculate the distance. Okay, so you get both the position and the distance. Okay, both the direction and the distance. Okay, so 2D radar works this way. You find the horizontal direction and the distance. In the case of 3D, you can also find the altitude. Okay, so we'll talk about that in our lab class. Here what I wanted to point out that in this case of radar is very important how much power you get back from the object compared to how much power was incident. Okay, depending on that, your radar will be more precisely tell you about the object. Okay, a lot of times radar has some fake detection, even from large birds. It can have some good amount of signal back, and sometimes there can be misfire. Okay, the defense may assume that there is a flying object. Okay, I mean from the enemy side, and this detection from the radar can cause some misfire. Okay, so but it might have been some large bird or some object. So anyway, so how much energy you get back, okay, can actually confirm uh, uh, whether it is can actually, I mean, if you have better signal back, then your determination, your decision will be more reliable. Okay, so it's very important that how much the object reflects. And the stealth aircraft, they their purpose is to reduce this RCS, the energy that is incident. Okay, I mean when it is well, when you ratio the energy with the when it is ratioed with the energy that is uh, scattered from the object. Okay, so this RCS is made too low, meaning that you will have very little amount of energy reflected. Especially it tries to deceive in a way that it has both ways of uh, techniques, like you it uses some material coating around itself, the stealth aircraft I'm talking about. Okay. A few countries have them, uh, on only a few countries, maybe 3 4 countries or 4 5 countries have them. China, USA, and few European countries. So they have some material coating around themselves, so which absorbs energy very well. And more importantly, they have some shape uh, which can deflect the energy in different direction or disperse the energy in different directions. Okay, so from reception you are confused. Okay, you don't receive good energy from any point. Okay, you're transmitting, and in the past the same transmitter and receiver, I mean the radar had the transmitter and the receiver located at the same point, at the same place. Okay, but this stealth aircraft can actually uh, deflect energy in other directions. So people also, the defense people also use the a different position for the receiver. Okay, but the stealth aircraft got more advanced. It disperse energy in many different directions. Okay, so anyway, so radar side has improved. Still, the aircraft has side improved. Both sides are improving. It's not that all the time they can deceive. Sometimes the stealth aircrafts are also detected. Okay, so anyway, the RCS is made lower in this case. So uh, you, in some cases, so for commercial airplanes, definitely you want to have good RCS. Okay, uh, but in the case of a stealth aircraft, you may want to make it low. Now, in the uh, case of our general wireless communication, we actually don't have any control on RCS. We rather want to estimate. Okay. And the discussion here targets the estimation. Like if you have some of buildings, large buildings, which are medium or large buildings located 5 to 10 kilometers away. then your RCS may range between 14 and 55. Okay, roughly. So it depends on the uh, uh, surface quality and also on the surface size. So for RCS, the unit is dB meter square, because the if you have larger surface, you'll have more energy scattered. Okay, so it's just a ratio that qualitatively, okay, tell you about the um, smoothness of the surface, okay, or how much it may scatter, and also uh, about, I mean, it includes the size of the surface, okay, I mean overall impact on the scattering. Now, how you calculate the receipt power? Eventually, we want to calculate the receipt power. Okay. In the case of diffraction, we showed how you consider the diffracted energy while calculating the receipt power. Here, let me tell you how you do that. PTGT is like before. Okay, 20 log uh, lambda. Okay, this part is like before. Now, the last few terms like RCS value you put here, then minus 30 log 4 pi, then minus 20 log dt. It is the distance of the transmitter from the scattering object, and minus 20 log dr. Okay, there is again the distance from the receiver from the distance of the receiver from the scattering object. Okay, so you put them and then you get the receipt power. The proof of the equation we are not showing. That completes our discussion on scattering. Any questions?
No, sir.
Okay, then we'll have another short discussion. Uh, this this way we could talk about the radio waves actually in the beginning of our course, but the reason I didn't do that this different modes of radio wave is no longer very important. Okay, I mean in the past they were, but now they are not. Well, when you launch the radio wave purposely for the purpose of wireless communication, you actually in the for terrestrial communication, you actually basically have three ways, okay, to communicate. First, you transmit, and the signal. Think of the radio broadcast. Okay, these radio stations have very wide coverage, but how the signal propagates? You have low frequency signal, which actually goes along the Earth's surface. It uses some diffractions along the surface. Okay, they keep propagating along the surface. The diffracted rays along the surface keeps propagating, and because of low frequencies, they can travel very far. They can cover even a small country, right? That's how people can use furtively. People can use radio broadcasting like Shadin Bangla Betar. The enemy people couldn't identify its location. Okay. So furtively you can operate, you can transmit some signal and it will propagate and cover a large area. The frequency range for this kind of communication, it is called ground wave propagation. The wave is very low, okay, say 30 kilohertz to 3 megahertz. The AM radio broadcast, okay, uses this, I mean, apart from this range. Well, but you know, this AM radio is no longer popular. In the past, I mean, these concepts, of course, we have. I mean, this is taking place for other types of communications now. Okay, uh, but this, I mean, thinking of the communication this way is no longer popular. Okay. Uh, Now, for long distance communication, you know, the early days of wireless communication was mostly radio broadcast. Uh, so this radio broadcast was also made possible for very long distance communication. For, you know, I mean, for some good coverage, quite a bit of large area you can cover using ground wave. But if you want to have an intercontinental communication, like we when I was I mean, young, but as a young kid. Okay, I mean, we used to hear two radio stations during some um, political turbulence or something. Okay, so when the local uh, media uh, was not allowed to convey the right message, so two stations, these are BBC and Voice of America. So these, I mean, from USA and from England, there were transmissions and we could hear. How was that possible? Using skywave propagation. What happens there? The wave can have a complete internal reflection in the ionosphere. Ionosphere is, you know, I mean, the some of the top layers, or one of the top layers of atmosphere. Okay, and as you can see, troposphere, stratosphere, and then you have ionosphere. So it is ionosphere because you have some uh, ionization there, and so these ions can create an area where you have good refraction, and this refraction, this high amount of refraction, and also you can see the ionosphere is pretty high. Okay, so this high refraction can cause a complete internal reflection, so allowing the signal to come back to the earth. So this way you can actually cover a very large range and intercontinental communication is possible. And also it is possible that you have a reflection from on the ground, because ground is a good reflector, and you have a second internal reflection. Okay, that uh, becomes very weak though, but it is not impossible. So actually this way, this is called skywave. This way you cover a large area. Of course, between ground wave coverage and your first skywave communication, there is a large area which you cannot cover. Okay, so this is called a skip zone. So is the, I mean, using both ground wave and skywave, you can cover a good part of the earth, very good part, but not the whole. Okay, especially mainly because of this skip zone. Okay, the frequencies that is suitable for this skywave is given here. It's little higher than ground wave. Okay, so 3 to 30 megahertz, which is high frequency, called HF. And the refraction occurs at layer E and F. Okay. However, at night, the skywave works better. Uh, you have, I mean, D layer doesn't absorb energy then. Okay, so it works better, and even for frequencies below 3 megahertz, some ionospheric uh, complete internal reflection occurs, and you can get some signal back to the earth. Okay. Thirdly, space wave propagation, which means what we have covered so far, what we have talked about so far in this course. Okay, I mean, you send the signal towards your receiver without considering the Earth's surface to take the signal or the sky wave. Okay, rather the the direct path. Okay, between them. Uh, well, so this is called space wave propagation. Question? Do you have any questions? I mean, this type of consideration of different modes, as I said, is no longer very important. Okay.
Sir, how do the people of the skip zone communicate then?
Please say that again. I couldn't quite
How
get.
do the people of the skip zone communicate then as they
Okay,
do?
they cannot. I mean, the BBC, Voice of America, this type of attempts could not cover the whole Earth. They could cover a good part. Okay, so this way people could uh, hear. The frequency range here is very narrow, 3 to 30 megahertz. So it's not that many applications you can fit in there. There are some, as I said, BBC, Voice of America, some radio broadcast stations used to use skywave. Okay, mostly that was the use of skywave, and they had coverage. They tried to cover the whole Earth, but every part could not be covered because of the skip zone. Also, I mean, we had to struggle a lot. The sound we could hear was mixed up with a lot of noise. It was really noisy. But people were also eager to hear the real uh, occurrences, what is really happening out there. So there was no other media which could convey. So people had to tune to BBC or Voice of America. That we had to do. In 80s, there are a lot of political occurrences around. So we all used to listen to BBC and Voice of America to get the right news. Okay, so every part of the Earth is not really covered. Okay, we'll go for a third small discussion. Give me a second. Okay, I hinted before. Oh, I'm sorry, but my internet got disconnected. Okay, I hinted before. Yes.
Before you proceed, sir, so could you repeat that part again, sir, regarding the uh, BBC and Voices of America once again? You got
Well,
disconnected at that moment, sir. Yes.
okay. I mean,
Yes.
in the case of political turbulences, uh, you cannot get the right news from the local media, and in many countries, and Bangladesh also had that. So I remember in 1980s, okay, uh, I mean, frequently different things happen around us. So there was no way we could get the right news except BBC and Voice America. So we had to struggle to tune to them. I mean, the sound is always noisy because this way the amount of signal you get is really low. I mean, the signal is really weak, and it is so your radio receiver has some noise. Okay, so the whole signal is SANR is very poor. So this sound we used to get is noisy, but we could still at least, I mean, somehow uh, understand what the guy was saying what the real news is, and that was important. So people used to struggle to listen. The sound was noisy, but they nevertheless they struggled because that was the only way to get the right news, to come to know what is really happening outside. Okay, so I mean, this kind of communications were useful. Okay, uh, because this I mean, all the different communications that we have today did not exist then. So people relied on this sky wave communication, but the sky wave cannot cover the whole Earth. Okay, so with these attempts, people could cover a good part of the Earth's surface, and many countries could be communicated, but not every part of the Earth. Okay, the escape zone doesn't allow that. Anyway, now we'll talk about unlicensed radio bands. I actually already hinted these facts that some small chunks. Okay, let me show you. So these are some frequency ranges which don't require licenses. You can use them in our country. And there's another set. These are the two sets which are unlicensed frequency ranges. Okay. However, these are internationally agreed on. However, all countries don't allow all of them. Okay, some of these frequency ranges are not allowed in some countries. So, if you want to use a particular frequency range in a particular country, you have to check. Okay, if it is allowed in that country.
Sir,
Yeah.
sir, the 5 gigahertz bandwidth that we use in
Yes.
our router, sir, which bandwidth is that in that other chart?
Yeah, I mean, there are actually these unlicensed bands are, of course, allowed for some purposes, and the most important one is ISM. The purpose when the authority allow these frequency ranges, they had these three purposes in mind: industrial applications, scientific, and medical. Okay, so there are a lot of medical devices that use wireless, so you don't want to take permission for the use of each of them. So these ranges are available, and later this another purpose was added: unlicensed national information structure. Okay, so some other frequency ranges are here also added. Okay, some of them are overlapping, maybe. Okay, I'm not sure. 5.8 through 725. This part may be little overlapping, this one, but anyway, so all these frequency ranges can be used without taking any license from the authority. And the original purpose was that it won't be used for commercial communication. Okay. But the fact is that in recent years, there has been growing use of these bands for commercial purposes, like say cellular guys, also Wi-Fi. Okay, Wi-Fi is not always, it doesn't always fall into these categories. Okay. These are mostly like humanitarian purposes. Okay. But the Wi-Fi a lot of times is used for commercial purposes, like all the commercial, the corporate people are using Wi-Fi. So it is sort of mixed up, but it is still allowed. Okay, it is not considered a violation, but it is actually a deviation from the original purpose of this permission. Okay, so when the situation has differed, okay, the large commercial operations have also started to use this unlicensed band. They're saying that why we are spending so much on the licensed bands, okay, and these uh, some other commercial guys are using, okay, they're making money without paying anything for the bands, okay, so why can't we also use that? Why are we not allowed? Okay, they also started to use them, and this is still not considered violation. Okay, like okay, but let me complete this part. For when you use these unlicensed bands, okay, you have to make sure, I mean, there is some power limit for each of the cases. So as long as you are within the power limit range, it is fine. And so this shows some example uses of these unlicensed bands. Okay, as you can see, 2.4 gigahertz is the most popular, but in recent years, 5 gigahertz band has got a lot of use. Just because 2.4 gigahertz band has become full, okay, it's overly crowded already. So people had to resort to 5 gigahertz bands. Okay, so some other bands are also in use in many applications. The credit cards are can be now contactless. Okay, you just bring it close to the device, and then the transaction can take place. Okay, so using wireless communication. So anyway, so these are this sort of household uses or small commercial uses or some research purposes. Okay, you can use all these unlicensed bands. This leads some other uses. Okay, anyway, you can read yourself. Now, I was saying that large commercial operations have also started to use this unlicensed band, and LT specifies this use with the title LT unlicensed, LTU. Okay, so it is already in the LT specifications, LTU. And but you have to be very careful. The key problem for unlicensed band is that it is free for everybody. It's not only free for you. You're not paying money for it. But you need to understand that other people can also use it. So there is a possibility of interference. There are chances that you won't be successful in your operation. Okay. So you have to check which part of the unlicensed band is free currently, and then you can use that. Like what our cordless phones do. Cordless phones are programmed with a good number of channels, so maybe 40 or something. So it keeps checking which channel is free. So it listens first the environment. So it checks which, if a channel is not free, so it uses another channel. It scans and checks and uses a free channel. So that is the, I mean, somehow you have to face or encounter contention there is a possibility of contention when a resource is made available to multiple people, then things can still work, but taking care of the probable contention. So LTU does that. Okay, it has some protocols which take care of the probable contention. There can be other uses. So what it uses is called LBT. Okay, the basic protocol is called license assisted access, LA, and it was first added in release 13. I mean, LTU was first introduced in release 13, and the contention protocol they use is called LBT, listen before talk. Okay, similar to what I have just explained. And to coexist with, I mean, just to take care of the contention. I mean, there can be other applications, other users. That's why you need it. Okay, this LA has further improved in the later versions like release 14, and then it was called ELA, enhanced LA, and in release 14 it had another step of major revisions. Okay, and it is called further enhanced LA, FELA. Questions?
No question.
Okay, now we'll start talking about the radio network planning, but in this case we will consider GSM. So you may just feel uncomfortable. 2G is already obsolete in our country, in many other countries already. So why we consider 2G? It's because the basic radio network planning concepts for cellular environment can be most easily explained with 2G. Okay, just to make it convenient for us. Also, and these basic concepts are still valid, and they will always be actually useful in all different generations, all advanced generations. Okay. Now, first of all, this whole discussion we will go through as an example of non-LS communication. Okay, our course needs to cover the different aspects of wireless communications, and we want to highlight what the challenges are. Okay, and so examples can better explain the challenges. So we need actually example for both non-LOS and LOS cases. For non-LOS, the most of the maximum amount of challenges, all many different types of challenges you get in the case of cellular environment, cellular application. No other application has so much challenges. So this will be our example for non-LOS communication. For LOS communication, we will use satellite communication, which has the largest communication distance. Okay, so that also for LOS you need high power, or I mean more advanced system when your receiver is located further. Okay, so that is why we'll consider satellite communication. Now, for if I mean there are different frequency bands declared. Okay, and when a country allocates frequency resources, the country first has to decide which bands they will allocate from. Okay, so like in our, so there are many different bands. If you look at, I listed the bands for LT in the early pages of my book, and there were 25 bands then when I wrote this book. few other bands were later added. Okay, I think it is around 30 now. So you see, I mean, the specification of a particular cellular technology includes some frequency ranges as the permissible frequencies for its operation. So these are large frequency ranges from which the country will allocate different frequency chunks to different operators. Okay, like for PGSM 900, this is one of the early bands. They have this 25 megahertz in uplink and this 25 megahertz 935 through 960 in downlink. Okay. The duplex spacing is 45. I mean, you see the spacing from.
So we cannot see your slides, sir.
Oh, really?
Yes.
Oh, I'm sorry.
No problem.
Oh, I forgot. Now you see, right?
Yes, sir.
So you see the PGSM 900 band, okay, has some frequency range for uplink and for downlink, each of which is 25 megahertz range. Later, so the early 2G deployment used this frequency, this band. So, but it was little enhanced. So another 10 megahertz was added to both uplink and downlink. So another popular band is 1800. Now, in our country, 2G used this 900 and 1800 bands, and these are the popular bands in Asia, Europe, and Australia. Okay, but North America uses some other bands. Now, a phone. Okay, we are talking about 2G days now. Okay, I mean these concepts also apply to other technologies. Okay, now consider 2G days. So the 2G phone, a 2G phone used to support some of these bands. 4 bands were popular. Many bands were actually specified for 2G operation, but globally, these 4 bands became more popular. Now, the phones that you purchase here in Asia, Europe, Australia, normally supports these 2 bands, 900 and 1800. And the phones that you purchase in North America normally supports only their bands. Their bands are 850 in there. It is around 850 and 1700, I guess. Okay. So the bands are a little different. However, there are phones with tri-band support or quad-band support. A quad-band support phone supported all these 4 bands, and if it is tri-band, then it is 2 from this 900 from one of the 2 trains, either North American trains or Asian trains or European trains. Okay, either you take 2 from one of these 2 trains and another band from the other train. Okay, so this way the tri-band phones were manufactured. Now, if you are in Asia and you first turn on your phone, it will scan the whole bands. It is supporting 900 and 1800 bands. So it will just scan, check the power level. Okay, sweep through the whole bands just right after you power up. And it will find out where there is energy. So there can be operations, say in our countries, 900 and 1800 bands are used. So all the operators, Grameen, Robi, all the operators have frequency chunks from these bands. And of course, some frequencies are left unused within these bands. So when the phone sweeps, it can find out where there is energy. So all the transmission area, frequencies from Robi or whatever the operators are identified. Then it further reads the transmissions. And if your SIM is from Grameen, okay, it finds out that we have signal from Grameen in this part. So it further reads the signal from Grameen and then registers with the Grameen network. Okay. These things we explain in detail in the cellular communication course. But basically, capturing the signal, okay, occurs this way. Now, if you have a North American phone, dual band phone, North American, then it doesn't support these two bands. So when you power up, it scans some other bands, little different bands. So it cannot find the signals of these local operators. And so this phone will not work here. Okay. Similarly, an Asian phone will not work in North America. However, if you buy a quad band phone or even a tri-band phone may work in some cases. Okay. So then that phone will work in both North America and in Asia, Europe. Okay. So because that phone scans all the four bands and checks transmissions. The frequencies, we probably discussed that. I'm not sure if we discussed or not. I don't remember. In the case of 2G, it uses FDMA, TDMA. Okay. We need to support many users in a cell. Simultaneously, they will make calls or they will use data. The way you connect multiple users together is first to divide the available frequency range into a number of small chunks. These chunks are 200 kilohertz wide. So this way multiple people can use. Okay, maybe in a cell you have 1 megahertz. So split into 200 kilohertz. So 5 chunks are available. Now each of these frequency chunks will be time shared by 8 people. So one after another, they'll be using each of the 200 kilohertz chunks. So if you have 1 megahertz, you have 5 chunks, but 5 times 8, 40 people will be able to actually use this resource. So they'll be able to make calls. 40 calls, 40 voice calls will be possible. Okay. And so it's a combination of FDMA, TDMA. The length of these time slots are fixed, 577 microsecond. So the whole frame, okay. After every 8, the whole thing is repeated. Okay. A user, if he is allocated 0 number slot, he will get again a chance here. So when you first make a call, the network sends you a message. It's called an assignment message. Okay, I can show you these messages. I captured in 2G days. I captured the messages. We have a tool. We'll demonstrate. We actually demonstrate that tool in the cellular communication course. But I can demonstrate few things also in this course here from the tool. So we can capture the signal using the tool. The tool cost, these tools are used commercially by the operators. When we purchased, it cost us around 6 lakh, 5 to 6 lakh taka. But it's for academic purposes, they gave us discount. Its actual price is around, I think, 13, 14 lakh or 15 lakh. Anyway, this, both in downlink and uplink, okay, at the 2 different frequency ranges, this time sharing take place. Well, for GPRS or edge, multiple time slots can be allocated to the same user. For voice users, GSM means you use only voice. For voice use, only one time slot is allocated. Okay, and it is good enough for voice purpose. But for data uses, okay, there is no limit. I mean, the requirement varies. So if you have high data requirement, then more time slots will be allocated. Okay, so 4 time slots, even 5 time slots can be allocated to a user. Okay, normally 4 was the maximum. Now, in each of the time slot, okay, 77 microsecond, you send your signal, and it occurs this way. Actually, the power level, okay, the power amplifier gradually increases the power. You have to have sufficient power for the transmission of the real bits. Okay, when you transmit the bits, the power level has to reach to a sufficient level. Okay, after completion, the power ramps down. Okay, all of a sudden the power level cannot go to 0 level for the amplifier. So within this region, you transmit. I mean, horizontal axis is for time. Within this center part, you transmit 148 bits. But out of them, this 57 and 57 carries the real information. Okay. For voice, it is the voice information bits. In between them, there's a training sequence, 26 bits long, which we spoke of during our discussion on fading. We said that you can set an equalizer at the receiving end to reshape, okay, the filter, and you actually can get rid of some errors. Okay, so in the frequency of selective fading environment can be better addressed this way. So this training sequence has some fixed bit pattern. Okay, other fields we are not explaining because 2G is not important. Now, the whole frequency range that you lease from the government, maybe say if it is 14 megahertz, okay, let's assume it is 14 megahertz. You need to cover, using base stations, the whole country. What do you do? We, for the time being, we consider that we have different cells this way, and at the center of the cells, we have base stations. Now, let's assume that we have 14 megahertz, and we split this 14 megahertz into 7 parts.